start recording.
Okay, I will begin with a brief review of Bloch's theorem. Okay, so first, the Bloch's theorem states that if the Hamiltonian commutes with all the lattice translation operators, like H with TA equals to 0 for all A be the lattice operator, then there exists a basis of eigenstates of the Hamiltonian such that the eigenvalue, this is the eigenstate of the Hamiltonian. And then because of this equals to 0, it implies that if you apply the eigenstate to the translation operators, it will get this form. And then because the lattice translation is like its reciprocal lattice is periodically repeated, so that the k is equal to k plus g. This is describes the same Bloch states. And it must satisfy this condition. A times g equals to 2 pi n, where g is the reciprocal lattice vector.
So I will just briefly replay this. Can you move to the side so people can see better? Be careful of the wire. So the point is, we have these translation operators. The translation operators, what they do, they act on a wave function by just sending psi of x to psi of x plus a, so just shifting the argument by some vector a. So if I have some lattice with vectors a, or in general, if I have some periodic potential, which is has a discrete periodicity with these lattice vectors a, okay, if it commutes, then I can find a basis of eigenstates such that they're simultaneously eigenstates of the Hamiltonian and eigenstates of these translation operators. Now, what we always want to do is we want to label the kind of states by the eigenvalues that they have. But in this case, we see that the eigenvalue has, with TA, has a very nice form. It has a form of e to the I dot k. So instead, we label the states using the kind of phase of the eigenvalue instead of the eigenvalue itself. Do you agree? And what you then realize is that in principle, this k, I could choose two different k's, which give me the same eigenvalue, right? And so, in principle, you could pick many different k's, which all give the same eigenvalue. And so that's why we often say that, okay, k is equivalent to k plus some vector g if g satisfies this condition. Because if you just plug k versus k plus g, you get that it has the same eigenvalue. And so it has to be the same state as far as we're concerned. Okay. Yes. So that's all we're doing. We just have quantum numbers, but instead of choosing eigenvalues to label our quantum numbers, we choose the phase of the eigenvalue to label our quantum number because it has a nice form like this. Okay, go ahead.
Okay, G is the reciprocal lattice vector. And this leads to us a property of defining the first Bernoulli zone. So if like if in the 1D reciprocal lattice, say here is like k equals to 0, and then because of this property, it means like G equals to 2 pi n over A. And then when A equals to 1, we can say that this is 2 pi over A, and this is like 4 pi over A. And then this is negative 2 pi over A, and this is negative 4 pi over A. And then the Pauli zone is it defined as that it is the perpendicular bisector between the origin and then every other reciprocal lattice that is closer to the and every other reciprocal lattice point. So, but the first Pauli zone is that the region is like that is the region is closer to the origin than any other reciprocal lattice point. So generally we consider the half of this length. So it's like here, and this region is the first Pauli zone.
Great. So once again, I want to label my eigenvectors by some number k, but I realized that two different numbers could, in principle, label the exact same vector. So I want to choose a domain. I want to choose a convention such that I'm looking at a certain domain which only has inequivalent vectors, so that I'm not kind of double counting things if I'm doing some calculation. And the way we do that is we have this convention of first zone, where you look at kind of the points when things start being inequivalent from the origin, and then you go look at perpendicular bisectors from that. Look. And that will be your first question. Okay.
And then also for the triangle lattice, it's the same idea. If it's like if I have these letters here and then here, and then it's you take the perpendicular bisector of this, so and then from here to here you go like this, and then from here to here you go like this, and then from here to here you go like this, and then from wait
you're
yeah
missing some, like you'll get
here should be like this. Oh wait.
maybe we can. So the important part is, yeah, just keep drawing.
Okay.
The important part is that for a triangular lattice, the reciprocal lattice vectors also form a triangular lattice. And so if you draw it very carefully, yeah, right. So just draw the perpendicular bisectors to every single one. Yes. There's a horizontal, vertical one. Yeah. There we go. That's right.
And then this region is the first Pauli zone for the triangle lattice.
Can you take a different color and just outline the edges of this Pauli zone, so that it's a bit more? Choose like red or something, or purple, because that's hard to see. But yeah, there we go. Like that. Like this. Yeah. So that's maybe actually that's a pretty good drawing. Like for a triangular lattice, at the end of the day, the first Berlin zone is a hexagon. Is what you get if you do this. And all this is saying is that if I have a triangular lattice and I want to label my states with a wave vector, right? And I want to do the same in a unique way, then I choose a region, which is going to be the first Berlin zone, which is a hexagon, and take vectors only from the hexagon, because the hexagon is kind of the region where all of the vectors are inequivalent to each other, and then everything outside is equivalent to something inside the hexagon via some reciprocal lattice. Okay? Yes.
Is it just like another way of labeling it, like compared to the last? Because last time we had like two sets of vectors, right? So like in that, like, is it something complementary or?
No, this should be all the same. What do you mean by? So last time we had real vectors in real space and then vectors in reciprocal space. Is that what you mean?
Like remember we had two triangles.
Ah,
Yeah.
yes, yes. So last time we had two triangles. Was it because we were talking about graphene or?
I think so.
Yes. So in graphene, the point was that you have a hexagonal lattice, which is two triangular lattices. You agree? So if you have two triangular lattices to make a hexagonal lattice, it doesn't matter because the periodicity is still a triangular periodicity.
Is that different?
Okay, this is a good question. I will explain. So here, what the discussion here was: suppose you had a lattice which looked something like this. Okay, suppose this was your real space lattice. Do you agree? Then I want to find reciprocal lattice vectors. Reciprocal lattice vectors. So say this. Suppose this is A1. This is A2. Okay. Suppose I wanted to find a reciprocal. Right. Suppose I wanted to find reciprocal lattice vectors. So reciprocal lattice vectors would be such that A dot G is 2 pi. Is 2 pi. So I want to find vectors such that G dot these things is 2 pi. Okay. The way you do it geometrically is you take something that's perpendicular to A2 and has the right length to get 2 pi I if you dot product it with this one, and then something perpendicular to this one. Okay. And so these are going to be my G2 and G1. Okay. And so then I can draw, using these G2 and G1, I can draw a reciprocal lattice with these vectors. Okay, something like this, whatever. Okay, and then I can do this construction and get that everything is labeled by stuff inside of a hexagon. Okay, all the inequivalent things are inside of a hexagon. Okay, now what we were talking about last time was we didn't just have a triangular lattice. We had in real space. We had a hexagonal lattice in real space. So we had a honeycomb lattice.
In which sides two triangular?
Pardon?
In which sides two triangular lattices, so they can regroup.
Exactly. So the point was that if I have a hexagonal lattice, that's the same thing as I have this, 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 and take this triangle and kind of copy paste it everywhere to fill space. And then I have this triangular lattice. Okay, do we have two triangular lattices? But what is one way to think of this? One way to think of this is, suppose I took kind of this point and this point, I took this bit, okay? And then I used these triangular lattice vectors to kind of translate this whole line segment from here to here to here and so on and so forth. And that way, I will be able to kind of hit all of the points anyway. So now I realize that this is kind of two triangular lattices, but it's really like it's a single triangular lattice, but made out of an object that has like 2 points on it. Do you agree? And so because this is still a triangle, the periodicity, periodicity symmetry is still along a triangular lattice, right? My translation operators are still the operators that use this A1 and A2 as the vectors, right? In the theorem, right, these TAs are still the ones from a triangular lattice. So even though this looks like a hexagon, the Brillouin zone is still going to be a hexagon as the same as for a triangular lattice. Okay? Because what matters is under what shifts is the system symmetric. And this is symmetric under shifts along the triangular lattice and not anything else. Okay? So yeah, all I'm saying is that even though it's a hexagon and not a triangle, it's symmetric under shifts from a triangular lattice. So this kind of bit is the same as for a triangular lattice. What changes though is that I kind of have more states in the same thing. Like every point corresponds to 2 different states. But okay, you'll talk about that maybe later or sorry, does that answer your question roughly?
Yeah.
Okay, and the same as the 2D materials, if my first bowling zone is like this, and then because it's like translational invariant, and then if this one is kx, and then this one is kx plus gx, and this is ky, and then if this is ky plus gy, and then if it goes further, it will like go back to this edge, so that this edge and this edge are glued together, and this edge and this edge are glued together, and can anyone like guess what shape will it be? If this edge and this edge glue together, and this edge and this edge glue together. What shape? Oh yeah, exactly. It's a torus.
So sorry, this is for a square lattice. If you had a square lattice, the reciprocal lattice is also square lattice. But we have, because of this condition, we get that, you know, there's some identification of the edges, and so this is technically a torus. Okay.
And then I will go through like the type binding model for the graphing. I will draw the type model first. And then I have this one. And then the first assumption for the tight binding model is that if an electron like here, and then it will like stay within the orbital of like closer to the atom, and then that means that the first assumption is like it's called the localized orbitals. And then because it stays like closer to the atom instead of like hopping to the other atoms, and then we can define our Hilbert space to be a span of a set of block states alpha n, where n is the orbital index, like inside each unit cell. And alpha is the orbital type, and I is the lattice index. So if I write like alpha n comma I, that means that it is the alpha orbital on the nth atom in the ith unit cell. And then because of
Wait, hold on.
Right.
So alpha is the orbital index, or n is the orbital index?
n is the orbital index.
So it means what type of orbital, or what? What do you mean by orbital index?
Like
So I think n is which type of orbital, like SPDF, and then
okay.
alpha is the atom on which it's so atom type, I guess.
Okay.
I mean, I'm guessing that would be the. If not, if we realize that's not the case, we'll fix it. So let's understand this in terms of the diagram, right? So the claim is we're assuming that the electrons are very localized, so they have to be kind of very close to the atom, and they can't be anywhere else. So based on that, we'll just say, okay, the Hilbert space then should be the electron can be in a state where it's on one of the sites, right? And it is in some orbital on one of these sites. And so then we come up with an indexing system. So let me add the cat here, where the n means so I means kind of which unit cell it is in. Alpha says which atom in the unit cell it is on, right? Because there is, this atom is not the same as this atom, because this atom has kind of neighbors here, here, and here, but then this atom has neighbors kind of in different directions. So you have to specify, alpha is going to specify which type of atom we are on the green sublattice or the orange sublattice. I guess it's not labeled here. Then n is going to specify which, I specifies which unit cell I'm in, alpha specifies which atom in the unit cell I'm in, and n is going to specify which orbital on the site I'm in, right? Because if I'm here, I could still be in like SPDF, whatever, P1, P2, P3 orbitals. Okay,
you want to specify the spin.
Okay, sure, you can also add spin indices, whatever. Yes.
Why do you care about the unit cell number? Because each atom, you can say it's in 3 of the unit cells because it's surrounded by straight.
Okay,
So
good point. This is not quite.
Why would you care?
Okay, this is not quite unit cell. You're right. This is I'm being a little bit unclear. So remember earlier I said that I can build the whole lattice out of like a line like this, and then the rest of the line is this plus some. Okay, let's use something. I don't know. Plus some lattice vector A, which is really, okay, let's do M1 A1 plus M2 A2, right? This is where M1, M2 are integers. So I kind of can build the whole thing out of this, okay? So think of so think of alpha as I'm on this one or on this one, that's what alpha tells me. And then I is really like a pair M1, M2.
So I is more like an atom position.
Yes, it's like more of an atom. It's a position of this group of atoms, and alpha is which atom within the group you're on.
Sure.
Okay. And n is the orbital. You look confused.
With me?
No, her. Does this make sense? Does not make sense? Also label this here, 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 and then the other one is. And for graphene specifically, it's conventional to talk about these as call these an A sublattice and a B sublattice. Okay, and so I don't know, maybe you chose this convention later or not, but then usually instead of alpha, people write for graphene specifically either A or B to indicate if I'm on the orange or on the green. Are you less confused? Yeah. And so now I just say that the Hilbert space are these states of, it's some wave function which is on these sites, and it's just the usual atomic orbital. Okay, keep going. Sorry.
Okay, and even though it's like stays within this atom, and then it will like jump to other atoms, so like different orbitals are different lattice size, like they do not significantly overlap. So if you write it mathematically, it will like this.
So we'll just kind of assume that all of them are orthogonal to each other.
Yeah. And then this is assumption 1. And then for the assumption 2 is like, because the electron will stay near the localized orbitals, we consider the Hamiltonian contains the it contains two parts. The first part is that it contains the on-site energy, is where where the electron, like on which lattice site it will contain on-site energy, and also it will contain a finite range hopping. And then we define epsilon n to be the energy of the nth orbital at a given site. So this means that the electron mostly sits at the electron mostly sit at one atom, but it can tunnel to a nearby atoms. So last time, do you remember that the Hamiltonian is like this? Okay. And then because right here we're consider like each lattice point have like several orbitals, so that we we modify this Hamiltonian expression to this. This is the on-site energy term, and then you plus the finite range hopping. So this means that at I site and n orbital, it will like hopping to the j lattice point of the mth orbital, and then this is the hopping amplitude, and then plus the on-site energy gets to the whole Hamiltonian.
All right, so let's just take a small pause. So the first Hamiltonian is, so once again, this is just kind of what the model describes. We're saying that if I have a lattice where the electrons are very tightly bound to the atoms, then it makes sense that the best thing they can do is kind of go from, if that's my Hilbert space, right, where they just can be on these sites, then the best thing that they can do is go from one site to another site with some kind of energy cost. Do you agree? And so then you say, okay, well, how can I write down a Hamiltonian for that? And that's just for the specific case of the graphene sublattice. That's that kind of hopping term, where so remember A and B are the green and orange sublattice, right? So let's say the first term I have AI dagger BJ. BJ, those are creation and annihilation operators, if people remember. So what BJ does is it kills a state. It kind of removes an electron from the jth site in the orange sublattice, and AI dagger creates a electron on the ith site in the orange sublattice. Okay, and so that's just corresponding to an electron hopping from the BJth site to the AIth site. Okay, and so then I need kind of the reverse hopping to also be allowed with the same energy cost. Okay, do you agree with this so far? Okay, and so I'm just saying that should be my Hamiltonian under these assumptions. Okay, and then the next line the first line that he wrote is kind of this hopping Hamiltonian for this graphene thing where I have an A and B sublattice, and so also this summation over I and j in kind of square brackets, that is conventional notation to mean I sum over I and j where I and j are nearest neighbors. So I sum over indices I and j, so positions of atoms that are nearest neighbors. Okay. Now H is right. The next Hamiltonian that he wrote is kind of a very general version that you would write for like some arbitrary lattice, where the first thing that I have is a on-site energy, so the energy that an electron has just due to being in an orbital. Okay, that's what that is. And then the second thing is exactly the same. I'm just kind of allowing hoppings between atoms, but now I'm allowing maybe not just between nearest neighbors, but also between second nearest neighbors and whatnot. So I have a T with more indices on. But the idea is roughly the same, right? I want to allow hopping, say, I want to allow an electron to hop from this side to this side, and this corresponds to I destroy an electron on site I, right? And then I create one on site J with some cost T. Okay? Do you agree? This is all this is saying. Okay? So essentially, tight binding models are models that deal with Hamiltonians of kind of this type, and this is the particular example for graphene.
For graphene, if you want like more than nearest neighbor hopping,
Yes.
and you would be hopping into the same type as your original one.
Yes.
And you would need like an A dagger A.
Yes.
Then
There's no problem.
oh okay.
I just write A dagger A with indices, and then it's just solving it would be a little bit more annoying, but otherwise it's the same. Okay. And I think last time when we considered it, we also we didn't care about like having different orbitals. We just kind of assumed that the electron's always in like the ground state or something, and didn't consider different orbitals. In principle, you could consider different orbitals, but often it's easier to just suppose you're in one single orbital, then kind of the on-site energy is just a single shift to the Hamiltonian, and you can kind of ignore this term, which is what's here. Yes?
What's the role of T again?
T is the energy cost to hop from here to here, or from here to here.
Fraction?
Hmm?
Is it a fraction?
Of what?
Just like a fraction of
It's a number. What the number is whatever. It's a number. It is an energy cost to go from here to here. It is some parameter which tells me, you know, how likely am I to go from here to here? How much energy does it cost to go from here to here? This parameter you determine from experiment. I think it's about 1.9 EV or something like this for graphene. Okay, maybe that's a complete lie, but either maybe 2.9. I don't remember.
And okay, and then the third assumption is that it comes from the lattice is translation invariant. So from this, we get that TA, and then that means that we can Fourier transform A to be from the real space to the momentum space. And then this allows us, instead of thinking like an electron like localized on one atom, we think of a block wave like a superposition of all the equivalent atoms in the lattice with a phase factor e to the ik times a. And then we can do this because like each block state contains a unique k because like the Hamiltonian and the translational vector is like can be simultaneously diagonalized.
Yes. So recall that last time what we said from Bloch's theorem that if my system is translationally invariant under some lattice of translations, then I should have some eigenstates like this. So now what we do is, okay, I know that I have these kinds of eigenstates in real space that I can work with. So let's try and find eigenstates that satisfy kind of the properties from Bloch's theorem, and hopefully my Hamiltonian, after I kind of go into this new basis, will be much easier to diagonalize, if not already diagonal. Okay? Does that make sense? So like, I wrote down this Hamiltonian, now I want to find the eigenvalues and the eigenvectors. Okay? From Bloch's theorem, I know that the eigenvectors have to have these properties. Okay? And so then I say, oh, what if I just took these like states and did a Fourier transform of these states? Like just took the state, summed up over a bunch of them with phases, so literally a Fourier transform. And the new thing that I get in the end is still a basis. You can check it, but it is, you get a new basis of the vector space. And then you say, okay, now let's try and write the Hamiltonian in this new basis. And it turns out that once you write it in this new basis, it's a lot easier to diagonalize. And that was expected from Bloch's theorem. Okay. So do people see what we're doing, like big picture? Yes? Okay, go ahead.
And then from that, the first term, and we use this property, we get that for the on-site energy term, it becomes
Oh, you're doing it in the most general way.
K is the crystal momentum.
Yeah. That's what we used to label the Bloch state.
And then because like of this property, each K is like different, so that we can choose a Bloch's each like Bloch state is like has different K values.
Okay.
And then for the hopping term,
it's more difficult. Do you have the expression written down for the general hopping term?
wait, I only like have the expression for the diagonalized one, like to get to the like the energy band.
Okay. You know what? Let's okay. You know what? Let's I want to write. Let me like write down an example, and then you can continue. So yeah. Let's see. So let's try and do it for let's try and diagonalize this, and I will very briefly show the point. Or do you even want to do that one? Maybe I should do something separate, but that's okay. So okay. So what did we do? We had our annihilation operators, and sorry, I had my annihilation operators for the A and B sublattice. Then what I'm going to do, I'm going to define, using a Fourier transform, these AK things. Is it's minus, okay, e to the minus ik dot r. Well, actually, yeah, of AI. Okay, similarly for this. Okay, maybe. Now, I can do an inverse Fourier transform. Actually, there should be a 1 over root n, where n is the number of atoms in my lattice. Okay, and now I should be able to express the AIs in terms of the AKs and the BIs in terms of the BKs. Okay, so this is given by just the inverse Fourier transform. AK sum over K. Okay, and then similar thing for the BIs. Okay. Okay. Maybe. Now, what you will want to do, okay, I have these AIs, BIs in terms of the AKs, BKs. Do you agree? My Hamiltonian was written in terms of the IJ, BIAJ, in terms of these, right? And I'm saying that if I go to this AK, BK basis, life will be a lot simpler. Okay, this is what we said by Bloch's theorem. Do you agree? So what do you do now? What is my next most natural step? I said if I go to k momentum basis, life will be simpler. So what do I do with this expression?
You just substitute everything.
Yes, right? I have this expression for I have this expression for AI BI in terms of the AKs BKs. So I just plug it in. All right? I just plug it in. I do some math. At some point, I need to use the fact that the Fourier transform of an e to the ikr is a delta function. And what I'm going to get in the end is I'm going to get some sum over k, which I can then write like this. Zero, zero, here I'm going to have, okay, it's going to be some number, and then there's going to be some number dependent on k, some complex conjugate of that number dependent on k. Okay, like if I do this correctly, if I substitute this in, use some identities to get rid of to kind of convert the sum over I and j into the sum over k. Well, sorry, to get rid of the sum over I and j, I will get something that looks like this. So what does this mean? This is a row vector, this is a column vector. If I just multiply this out, right, this is just going to be some expression that I get. Right? This is just a more convenient way to write it down. Do you agree? Okay, very good. And now, as you can see, look how interesting. See, this is k, this k, this is k, this is k. All the k's are the same. Do you agree? Before here, I, j, these I and j are not necessarily the same. Now all of the k's are the same. Do you agree? And now I just have some matrix where if I diagonalize this matrix, I will get something that's clearly an eigenvector. Do you agree? So now the energy bands are just going to be the eigenvalues of this 2x2 matrix. Okay? And this is, so finding the eigenvalues of this 2x2 matrix looks much simpler than dealing with, whatever this is. Okay? Right. Why is this a 2x2 matrix? Why is there 2 degrees of freedom? Not Mura. Someone else. Why is it a 2x2 matrix, not a 1x1 matrix, not a 3x3 matrix? Where did the 2x2 come from? What's the basis? Some A's and B's. Yes.
We have it's these two triangles.
Exactly. That's exactly right. The reason why it's a 2x2 matrix is because I have kind of 2 inequivalent kinds of sites, right? I have like an A flavor and a B flavor. Do you agree? So it becomes a 2x2 matrix. Okay. If I included spin, it would then be a 4x4 matrix, right? If I had a different lattice, which had, instead of having 2 atoms translated everywhere, had like 3 atoms translated everywhere, then I'd have a 3x3 and so on. Sorry. Okay. I don't think we've just done this, written this down explicitly before. So. Also, I think for the rest, talk about one of the symmetries, and then we can forget the rest, or we'll talk about it sometime next time.
So one property of the 1D tight binding model is that the inversion symmetry.
Yes. So hold on for a second. Finish writing this, and then state what the setup is for a 1D tight binding model. Right? So draw a picture of the setup.
here is like the 1D type binding model, and then from
So
here,
suppose we had a one-dimensional lattice, and then you still have the same Hilbert space indexed by whatever, and then I can hop between atoms, and so my Hamiltonian looks exactly like that. But I think here you also have two different sites, right? Like the green and the white are somehow different.
yes.
Okay.
If this one is like A, and then this is
Yes.
like B, and then this represents like different different unit cell of the 1D type binding model.
Okay.
And then the intuition is that for the inversion symmetry, we have the I to be the inversion operator. And it's if I like insert this to alpha m, where alpha m is like the real space local orbital basis, and then if I like insert beta to the alpha m, this means that the m, because the inversion symmetry, the m will becomes negative m, and then because like if I in one unit cell A and B, there's multiple orbitals, so we have to like sum up all the beta orbitals so that we can define this to be I beta alpha. This is the matrix elements, so that this whole thing becomes
Okay. So that's just you're writing something down as a matrix.
yeah. And then if I act the inversion operator onto the block state, and it will
This is not a block state. This is a real space. Just
yeah. Wait, can I erase this?
Go for it. Yeah. I'm not sure.
Wait, let me write. Yes, and then for the inversion symmetry, we have the condition that the inversion
Hold on,
operator
hold on,
with
hold
the
Hold on. You still haven't defined what the inversion operator does. What does it do?
um
What you wrote down is you just wrote down, oh, I can write it down as matrix element. Can someone tell me what the inversion operator should do? It's in the name. The inversion operator should do what? Yes, invert. Invert what? Okay, just look at what I'm doing. Hmm? Yeah, it should take the lattice and kind of send it to the opposite. So let's okay, so this is something very general with very many indices, very complicated. Let's look at a much simpler example. So suppose I have this kind of lattice, right? And okay, suppose I choose like some center of symmetry here, okay? Then the inversion operator, it should say send the site of flavor alpha in the nth position to the site of the same flavor in the minus n position. So it would kind of take this, send it to here, take this, send it to here, and so on and so forth, right? I can define an operator like this. Do you agree? I just did. Okay, let's call this the inversion operator. Okay. Now, I think what you're about to say is, suppose I acted the inversion operator on a state with on a state of flavor alpha with momentum k. Do people remember how this was defined? Okay, what was this? What was this? How do I get this state from this one? I sum over n and do it. My ik dot what? R, but what's the r's? Dot the position, right? See, I'm in this. I'm here. This n is used to refer to 1, 2, like the position of the atoms. Okay, so it would be ik dot n or r sub n, whatever. Okay, alpha n. Okay. Now, if I apply this I operator to it, okay, it does nothing to the exponential because that's just a number. It acts on the state, and I'm going to get what? Sorry, I think you maybe were going to say this later, but I'm already here, so it's too late. It does what? It's going to send alpha to minus n. Do you agree? Do you agree with this? Where? Oh, yes. That's right.
Shouldn't it be IKR instead of negative IKR? Because you're writing momentum either state in the position.
Whatever the convention. Oh,
Yeah, I think so.
oh yeah, you're right. No, it is a convention. I can always define my Fourier transform with flip side. So, yes, there was no minus.
Take the momentum operator, you get the wrong eigenvalue.
Okay, change the convention for the momentum operator.
Okay,
Quit
sure.
complaining. Okay.
Divide by root n.
Yeah, there's a.
Yes, that's right. 1 over root n. That's right. That's good. The root ends always like cancel out in the end, so it's like I just don't write them half the time. Okay, good. But now what you can realize is, hold on, I'm summing over n. I can kind of send n to minus n, do you agree? And get 1 over root n, n e to the minus ik dot n alpha n. Right, so I didn't do anything, I just changed the order of summation. Okay? But this state, you can see, okay, wait, this is alpha n. Okay, I just have a minus sign from what I had before. So how does this new state relate to this old state? Question for Thomas. How does this state relate to this old state? So what I got here, what is it?
Is it just like alpha, comma negative k?
That's right. Alpha minus, okay? Do you agree? So we get that, what does the inversion operator do on momentum states? It just sends their momentum to minus of itself. Okay? Was this expected? Yes, because I mean, I just took like, I took my space and then reflected it. Okay, and so my momentum also got reflected. Okay, so this inversion operator, we can define it like this. Okay. Now, suppose that what? Sorry,
Yeah, and then
interrupted.
now it's like from here equals to 0, and then if you write it another way, it's like this.
So suppose our Hamiltonian had an inversion symmetry. Yeah.
And then we have to show that this equality holds. We have to show that this equality holds, and then in a block basis, like define this, we define the Hamiltonian matrix to be this. And then if you plug in this to And then from this side, you get that you just plug in this to this, and then you finally you will get this term. And then if you like rewrite this into like other variables, you get that this. This is just equals to a summation of the this is just the left hand side, and then
Okay.
for the right hand side, you you plug in this equals to this term, and then and by the definition of the h negative k wait.
Right, so what are we supposed to get in the end?
At the end, we're supposed to get this.
Okay, but what does this tell me? What's particularly interesting about it?
It tells that the energy is like the set of energy of the ENK was equals to the set of the n negative k.
Yes. So, but you know, you're doing this very long calculation in components, and I don't think that's strictly necessary. So just to kind of illustrate this fact, right? So if I know that the inversion commutes with I, do you agree? Then I have this, right? So this I know. So suppose I know this. And suppose I look at some momentum state K. Do you agree? What I just saw is that well, it's erased, but we saw that I sends the state with momentum K to a state with momentum minus K. Do you agree? Right? This is what we just. So then, if I just compute this explicitly, right? So if I apply H to K, suppose this is some energy eigenstate like before. So this is just going to give me I times E sub K, well, E of K, K, do you agree? But then I, so this is a number, I does nothing to this. I applied to K gives me E of K times minus K. Do you agree? Okay. So this is if I apply this on this side. If I apply K on the other side, do you agree? I'll have HI applied to K. But that's HI, but that's H applied to minus K. And that's equal to E of minus K applied to minus K. Do you agree? But I got that this side has to equal to this side. So I get that E of K has to equal to E of minus K. That's it, right? And so what does this say? This tells me that in some sense, if I have some kind of symmetry of my underlying lattice. Right? In a tight binding model, that would lead to some symmetry of the Hamiltonian for this lattice. Right? So this means that the Hamiltonian commutes with some operator, but then that actually tells me something about how my spectrum of energies has to look like. In this particular case, I know that if I was to plot this spectrum of energies, if I have an inversion symmetry, it has to be symmetric around the origin. Okay? For example. Good. The other thing is, actually, this statement is a little bit different from this one. It's not quite the same, because this I think here you actually have to be kind of careful about how you're what states you're acting on with what. But essentially, yes.
Since when is the Hamiltonian dependent on K? So I think you need to have a transform.
Yes, exactly. So this is exactly right. This is something that was not said explicitly. So see here how I rewrote my Hamiltonian as a sum of these things, as some sum of these terms that are indexed by K. So this individual term is what we call H of K. This individual term is what we call H of K. And so in that case, you can think of your Hamiltonian as some sum of these other kind of block Hamiltonians, which act on some subspace of your Hilbert space. Okay, and so in that case, this has this has some meaning to it. My Hamiltonian, I can express it as a sum of these different Hamiltonians, and I realize that H of minus K is actually related to H of K in some particular way, thanks to my symmetry. Okay, I think we're kind of close to running out of time. Can you tell us what the next symmetry is? And just don't do any calculation. Just tell us what the symmetry is, what the operator for that symmetry is, and what the final outcome
Okay.
is. Maybe erase the second word and and for example okay, just keep going. And so, for example, actually, never mind. Sorry. I mean, this is also sometimes helpful in calculations, right? If you know that if you were to reflect along some axis, right, your energies will be the same. This means that you only need to compute energy in like half of the Brillouin zone, and now the other half, because the other half you'll get it automatically by symmetry. For example. Oh, is time reversal the other one, or is there
The spinless particle
without
spin.
Yeah. Is there another one though?
No, there's a spinful particle.
Okay. Then let's just go with time reversal.
So if we like consider a plane wave like this, this is the time reversal operator. If you act on this plane wave, you get that this is e to the negative I px, which is the complex conjugate of e to the I px, and then this means that t equals to k, where k can be written like this, and then at the end, if you do the time reversal operator act on the block states, you finally get that this. And then Yeah.
Yeah, so let's just put the comment. What time reversal symmetry does is it's a kind of a bit complicated, but time reversal symmetry is if you write down the usual Schrodinger equation, maybe for just wave functions, and you send t to minus t, okay, and also you complex conjugate the wave functions. So essentially, what you'll get is if psi of tx is a solution to the Schrodinger equation, then psi complex conjugate of minus tx will also be a solution to the Schrodinger equation. And so that's precisely this symmetry. This symmetry operator is something that takes this state and sends it to this one. So we can define an operator like this. That's this T operator. It turns out that this operator on momentum states will do this thing. It will also just kind of reverse momentum. That's also expected. If I change the flow of time, then my momentum direction should just also change in the opposite direction of time. And okay, now suppose that this operator was a symmetry of the Hamiltonian, then what?
Then we have like the constraint on the block's Hamiltonian from the time reversal invariance means that this is equals to the Hamiltonian times the time reversal operator, which is the same as this. And then if you act on and then if you like do this, and then you act the left hand side on each of the block states, and then the right side the same thing, and then after you do that, you finally get that T, the time reversal operator times the Hamiltonian times the inverse of the time reversal operator equals to the Hamiltonian of the negative k. You finally get this.
Okay, somewhat similar to what we had before.
And then this is and then we often write like this was equals to like this. Yes, I think that's the final.
Yeah. Okay. So there's actually a little bit. It was a little more subtle than that. So with inversion symmetry, we already had the first step, and in the case for time reversal, not only did you have this, but you also got that the complex conjugate of this was equal to, oh yes.
Yeah, I read it here.
Sorry, you wrote that.
Yeah.
So yes, so in time reversal, even though it looks kind of similar, you get this additional constraint on what the on how like different parts of the Hamiltonian are related to each other. Yes.
Isn't that always true? Isn't Hamiltonian solution?
No, but this is h of minus k.
Oh,
right?
Okay.
So this is kind of a different thing altogether. And also, this is just a complex conjugate. I just complex conjugate all the entries. I don't transpose them. Okay, right? So this is not necessarily guaranteed, but it turns out if you have time reversal symmetry, it is guaranteed. Why is this interesting, and why am I mentioning it? Later, when we start talking about kind of how topology enters and all of these things, we will kind of build our vector bundles out of the eigenspaces of this Hamiltonian. And if we have certain symmetries, we'll realize that actually some of these eigenspaces are kind of related in a very simple way. And essentially, we'll get that if I have a lot of symmetry, then, well, I think actually, if I have exactly inversion and time reversal symmetry together, then I don't get any topology, particularly because the eigenstates are kind of related in a very simple way to each other. And so I kind of need some of these symmetries to not be there or be broken in some way to have some kind of interesting topology of K. Okay, but for now, these are just kind of very vague words. We'll see exactly how this appears later. Okay, thank you. Now, you don't